This is a video for section 6.3, properties of integrals. We're actually going to start with a question not only tangentially related to calculus. If I gave you f of x was x squared minus 5x plus 7, what is f of t? This question kind of confuses students at first because they're like, I don't know what f of t is. I don't see any variable of t. It's really not hard. If I asked you what f of 0 is, what would you do? Well, you'd take 0 and you'd plug it in for the x's. So instead of x squared, you'd have 0 squared, minus instead of 5 times x, you'd have 5 times 0, and then that plus 7, and you'd calculate that all out, and you'd find f of 0 is equal to 7, right? F of t, no different. Instead of plugging a 0 in, you're going to plug a t in. So f of t would be t squared minus 5 times t plus 7. Finding f of t when you already know f of x is just rewriting the same equation but with a different variable, a variable called t instead of a variable called x. It's something you don't typically see because why would you want to do that, right? It's the exact same function. If I graphed this one and it looks like, let's say it's a parabola, it probably looks something like that. If that's f of x, where this is the y-axis measuring f of x, and this is the x-axis, graphing this would be the exact same thing. It'd be the exact same graph. The only difference is now this would be the t-axis, measuring how t changes. This would be f of t, right? So normally there's not any reason we'd want to change a variable like that, which might be why it seemed hard and weird and confusing, because why would you do that, right? In truth, we normally don't. But I bring it up because it's going to lead us to a property of integrals. If I told you that I had some function f of x, and I knew that when I took the integral from 0 to 6 of f of x dx, I got 24. And then I asked you, oh, by the way, what is the integral from 0 to 6 of f of t dt? Well, f of t is going to be the same equation as f of x, just a different variable. So when you find the area under the curve, it's going to be the exact same area. This is a problem that sometimes shows up on the AP exam, not very often, but it has to do with something called dummy variables. So a dummy variable isn't a variable that's dumb. A dummy variable is a variable that appears in a calculation only as a placeholder and which disappears completely in the final result. So here, if I'm trying to find this, that variable really doesn't matter whether I call it an x or whether I call it a t. The final result is 24 either way you do it. So dummy variables are variables where the way you name the variable really doesn't matter because it's going to disappear once you perform your calculations anyway. In your book, I don't know the name of the property. They didn't give it a name, but I call it the dummy variable property because it involves dummy variables, saying if you calculate the integral of f of x dx or f of t dt or f of u du, it doesn't matter what you name the variable, the result of that calculation will be the same. All right. Let's go on to some more interesting properties of integrals. So, real quick review. We should know what this integral means. The integral from a to b of f of x dx just finds the area of f of x, of that function f of x. So it finds the area under f of x between a and b. So it finds this area right there. That is what an integral measures. All right. So with that in mind, maybe pause the video and see if you can figure out what this integral will equal. Hint, it doesn't matter what f of x is. Pick any function you like, nor does it matter what a is. Pick any function you like. All right, the answer is 0. The reason the answer is 0 is whatever function f of x looks like, I have no idea what it looks like. I'm just going to make something up. There's f of x. And no matter what a is, let's say a is right here on the x-axis. Doesn't matter. If I'm trying to find the integral from A to A, well, that means I'm going to find the area that starts at A and ends at A. I'm looking for the area that has absolutely no width, right? How much area is going to be right there? No area, right? It's got a height with no width. So the height of whatever it is times a width of 0, that's going to be 0. So this property is called the zero property. It says that the integral from A to A of f of x dx is equal to 0, no matter what the A is, no matter what the f of x is. Some people like examples for these. If you wanted an example one, I could say, I don't know, say we got the integral from 7 to 7 of x squared dx. All right, well, that's going to look for the area under x squared that starts at 7 and ends at 7. There's not going to be any area there. That's going to be equal to 0. All right, that's the zero property. Slightly more interesting than the dummy variable property. We're going to keep getting a little more interesting as we move on. This one's going to lead us to our next property. If I told you that the integral from 0 to pi of sine of x dx is 2, so I'm telling you that this area right there is an area of 2. What is this area going to be? Which would be the integral from 0 to pi of 4 times sine of x dx. Well, how does that 4 change this function? It stretches it vertically by a factor of 4. So all the heights here are 4 times taller. Well, if the heights are 4 times taller, that's going to have 4 times as much area. This one had an area of 2. This one's 4 times taller, so that's going to have an area of 8. All right, this is going to lead us to the next property, which is slightly more important yet. It's called the constant multiple property. All it says is that if you've got some constant like k, you can put it inside with that integral or outside of the integral. It's going to be equal no matter what. So for an example here, I've got the integral from 0 to pi of sine of x. I've got the integral from 0 to pi of 4 sine of x. I could rewrite this as 4 times the integral from 0 to pi of sine of x dx, and it's the same exact thing. You can move that 4 inside that integrand or outside. It's going to be equal no matter where you place the 4. Only if it's a constant, right? I can't take the sine of x and move that out there, just the constant. So an example for that, if you'd like examples, let's say I've got the integral of, I don't know, 10 times x squared dx. That's going to be exactly the same thing as 10. Oops, I've got some, let's say we're going from 0 to 1. That's going to be the exact thing as 10 times the integral from 0 to 1 of the x squared dx. Right? I can put the 10 on the inside of the integral, I can put a 10 on the outside, doesn't matter. The reason this property can be a little bit more useful is if you happen to know what the integral from 0 to 1 of x squared dx is, that would be 1/3. Then you can find this out, right? Because you say, well, that's going to be the same as this, and I know that thing. So it'd be 10 times 1/3, and your final answer would be 10/3. All right, so being able to take that constant and move it to the outside, it can be really useful. Moving on. This is going to lead us to another integral property. Here, I'm giving you a couple of bits of information. I'm telling you the integral from 0 to 5 of x dx is 12.5. You didn't need me to tell you that because you could see it's a triangle. You could probably have figured out that area yourself, but I'm telling you, it's easy. That's 12.5. And then I'm also telling you the integral from 0 to 5 of just 2 dx is 10. And again, you probably didn't need me for that, but I'm telling you anyway. This thing has an area of 10. So then the question is, what is the integral from 0 to 5 of x plus 2? These ones added together. Well, it's going to be that total area added together. It's going to be 22.5. The reason why, I'm going to color code this. I'm going to change this color to that color. The reason why is because that area of 10 is still right there, right? There it is right there. And that triangular area of 12.5, well, that's still right there too. So when I wanted to find the area of the two added together, it's going to be the same area of these two individually added together. That property is given a name. It's called the sum or difference property. It says that if you have a sum or difference of two different functions, you could rewrite that integral as two separate integrals with that same sum or difference. So for example, let's say we've got the integral of, I don't know, 3x squared plus e to the x dx. And let's say that's integral from 2 to 10, whatever. I could take that integral, and if I wanted, I could rewrite this as two separate integrals. The integral from 2 to 10, 3x squared dx, plus the integral from 2 to 10 of e to the x dx. Right. So one of the properties of integrals is if you have a sum or difference, you can split that into two or more integrals. Whew, lots of properties. We're burning through them. Let's figure out what else we got. Then we'll actually get some example properties. All right, so here we've got an integral. Oh, this part's important. X squared over 9, x squared over 9, same function. The difference is the first one is the integral from 0 to 6, and the second one is the integral from 6 to 9. So when I take the integral from 0 to 6, I'm finding the area starting at 0 and ending at 6. I'm finding that area there, and that area is 8. When I take the integral from 6 to 9, I start at 6, I end at 9, I find that area right there. That area is 19. So the question is, what is the integral starting at 0 and ending at 9? Well, that'd be all of this area starting at 0 to 6, plus all of that area starting in 6 and ending at 9. So you add them together. 8 plus 19 is 27. That's called the additivity property. All it says is if you got some integral that starts at A and ends at B, and then goes from that same B and then to a new one C, that's the same integral as from A straight up to C. Quick example, let's say I've got the integral from 2 to 8 of, I don't know, natural log of x. And I'm adding to that the integral from 8 to 12 of this same exact integral of the same natural log of x dx. As long as these things are the same, and this goes from 8 and that starts at 8, this will be the exact same thing as taking the integral at your very first starting point of 2 and going all the way to the last one of 12 of that same natural log of x dx. All right, I think it's time we actually do a problem that involves some of those properties. This is where it sometimes gets tough for students. They read this, it says for positive real numbers, a less than b less than c, and then they give you a bunch of integrals. This integral is that, this integral is that, this integral is that, and they ask you to find the last one. They say, find this integral. Students will sometimes stare at it like, I don't know where to start. That's a lot of information, and they kind of get overloaded. So I did have a hint down here that I normally can pull out when I have a smartboard, but I don't have a smartboard. The hint when you are kind of overloaded by a bunch of different stuff like that is to just sketch a graph, because that graph can help you out, help you make sense of it. So all of these involve some function called f of x. Now, I don't really know what f of x looks like. Excuse me. So I'm just going to make a sketch and say it looks something like this. Whatever. Maybe I'll have to adjust that sketch later. But I've got some f of x. And then it gives me some information. What does this information tell me? Well, it says when I take the integral starting at sum a and ending at b, I've got a total value of 5. So if I start at a and end at b, this area here has an area of 5. All right, so that's something I know. What does this thing tell me? Well, that says when I start at b and go all the way to c, I've got my integral is equal to 7. So here's b. I've already got b there. I know c is bigger, so c is over here somewhere. And I know when I find the area between b and c, that's going to be a value of 7. All right, I feel good about that. And then the last thing it tells me is the integral from 0 to c is negative. How do I get a negative value? The only way I can get a negative area is if the integral dips below the x-axis. So I'm like, here my sketch might kind of fall apart a bit. So I gotta say, all right, when I started at 0, let's put 0 over here. I definitely had some negative area. So let's say, I don't know, let's say my function actually looked like this. Maybe I'll even cross right at a just to make it easy to see. I don't have to, but I will. There we go. Sure. Let's say that's my graph. That value is positive. That value is positive. This area right here, that's going to have a negative value for the integral. But careful, it's not -2. -2 is the value of the integral that starts at 0 and goes all the way to c. So whatever number that's there, it's negative enough that it makes that entire thing negative, right? If I took this one and I added that and I added that to it, the end result is -2. So what value is going to be there? We got a 5 there and a 7 there. 5 plus 7 is 12. This stuff in here must have been a -14, because -14 plus 12, that would give me the -2. Now, again, I can't stress enough. Yes, there isn't any such thing as a negative area. You can't have a negative area, but integrals can be negative. So when I write that -14 there, I'm thinking about that's got an area of 14, but the value of the integral would be -14. All right, now let's look at my question. The question is asking, what is the integral from 0 to a of f of x dx? That's what I just found. The one that starts at 0 and ends at a. That is -14. All right. One or two more properties. This one gets people a little bit. It's asking, how does the integral from b to a of f of x dx compare to the integral from a to b of f of x dx? In other words, they're flip-flopping those limits, the upper and lower limits. All right, well, let's look at this. If we assume a is smaller than b, when I integrate from left to right, those x values are positive. So when I do that integration, I'm going to get a positive value for this area under here. What would happen if instead I integrated in the opposite direction? Well, going backwards, all of a sudden I'm going to have kind of like a negative movement to the for the x. So I have a negative direction this way and a positive direction that way. A negative times a positive is a negative. If I go in the backwards direction, let's say this area was actually, we'll make something up. When I go in the positive direction, let's say I calculate this area, and we'll just say that was an area of 20. Well, if I went in the opposite direction, if I went in the negative direction, I'd calculate those areas, but these widths would all be, those would be like negative x values going to the left, positive y values going up, calculating the area of those rectangles, it's going to give me a negative value for the integral. So if I do it backwards, I'm going to get the same 20, but instead of a positive 20, I get a negative 20. So what happens when you reverse the limits of integration, that a and that b? You end up with the same exact answer before, but negative. So when you have a b to an a, that's the exact same thing as flipping it from an a to a b, but then you have a negative result, an opposite sign. So an example, if I asked you to integrate, let's just do x squared again, and I asked you to integrate it from 10 to 1, that is a weird thing to ask you to do. We normally don't do it from 10 to 1. I mean, this is literally called the lower limit of integration, and that's the upper limit of integration. So asking you to do that is just a weird thing to do. You can do it, but it's weird. So if ever you see something like that, you're like, the integral from 10 to 1, that's weird. I would really rather calculate the integral from 1 to 10 of x squared dx, because that'd be a lot easier for me to calculate. Not a problem. If you flip those 1s and 10s, it's going to be the same answer before, but the opposite sign. Another question. Let's try this one out. For positive numbers a less than b less than c, they gave me a bunch of data again. Again, drawing this out might help you figure it out. All right. So I've got some a, which is less than some b, which is less than some c. I don't know where they are, but I'm going to put them here, a, b, and c. And then I'm given some integrals. The integral from a to b of f of x dx is 5. So that's positive. I do have some negatives, but let's see. Is this the same as before? 5 and 7 and negative 2. This is the same one as before, isn't it? 5 and 7. And yeah, look at that. This is the same situation we had before. Let's do the same sketch then. So I've got some negative values, some positive values, sure. And we already found that the integral from a to b is 5. The integral from b to c is 7. The integral from 0 to c is negative 2. So we had found out that this is going to be a negative 14. So that the overall integral from 0 to c is negative 2. Let's see what it's asking. Oh, it's asking for the integral from c to a. So from c to a, I didn't even need this one. From c to a would be the same integral as from a to c, but backwards, right? So this one would be the same as the negative integral that starts at a and goes to c of f of x dx. So we normally like to have the lower limit of integration on the bottom, so I like flipping them. If I flip them, I got to put this negative out there. And I can say, all right, well, the integral that starts at a and goes to c would be all of this area, which would be a total of 12. So this would be a negative, because of that negative, 12. All right, the last two properties are fairly minor properties and are not as important as the other ones. The first one is called the max-min inequality. It talks about some maximum and minimum values of f being between an interval a to b, and then it gives you some inequalities. It says the minimum value times b minus a is going to be less than or equal to the integral from a to b, which is going to be less than or equal to the maximum value times b minus a. So to show why this is true, I've got a little picture here. Where in this picture do I see that? All right, well, that's the integral from a to b of f of x dx. So that would be the area shaded in green there. So this is just that area shaded right there. Let's talk about what this means on the left-hand side. This takes the minimum value of f times b minus a. Well, on the picture, I can show that area. The minimum value looks like it appears right about there. That's the smallest A gets. So if I take that minimum value and I multiply it times B minus A, well, B minus A would be this width down on the bottom. And that minimum value is that height right there. It forms a rectangle here. And it seems pretty clear that if I take the minimum value times the B minus A, right, that width, that's the minimum times B minus A, that's clearly going to give me an area that's less than the area in green there, because there's going to be some value higher that goes above that minimum, right? And then this one on the right, let's see if I can do, I'll do that in this color. This one on the right is the same idea, except it's a maximum value of F times B minus A. Well, the maximum value, let's see, on the graph, I'd say that's right about here. If I take that height, the max value, times the same B minus A, I'll get this rectangle, which is clearly larger than both of the other two. So that's all the min-max says. It says that if you know the minimum of some function and you know the maximum of some function, the integral is going to be stuck in between the minimum times B minus A and the maximum times B minus A. All right. Last one is called the domination property. Terrifying name, not too bad. All the domination property says is that if you know you have some function f of x that's greater than or equal to g of x, then the integral from a to b of f of x is going to be greater than the integral from a to b of g of x. So if I wanted to show that in a picture, let's assume this function here, let's call that one g of x. What this is saying is if I knew I had some f of x that was larger than g of x everywhere on that interval, larger meaning it's higher up on the y-axis, I'd have some function like this, right? Always higher or greater than g of x. It's never going to dip down below there because then it'd be less than g of x for some period right there. So it's always greater than g of x. So it's always above g of x. If that's true, well, when I find the area starting at A and going to B, there's A and then B, that area under the curve is clearly going to be larger or a greater number than the area provided by g of x. All right? That's all that one says. Domination property. Whew. That was a lot of properties. I would recommend you kind of take notes on that, have the notes handy when you do the homework, but mostly a lot of it you can kind of figure out as you do it. So here are the homework problems. Give those a try. Try to do it with these properties maybe accessible, but not staring you in the face. Because a lot of times properties, especially in general, you kind of just want to get used to them and say, oh yeah, that makes sense. I can figure that out on the fly, instead of spending time trying to memorize properties without understanding them. If you understand the properties, you don't really have to memorize them. You can just look at the problem and figure it out like, oh yeah, okay, this is going to be true. So give those problems a shot. There are some review problems I'd recommend if you want to do it. So there is an optional review. I'd recommend problems 4, 6, 8, 9, and 10 of the quick review. So in this section, there's a quick review. If you want to do those optional problems just to refresh your knowledge on derivatives, might not be a bad thing because you need to keep that derivative knowledge fresh. We're going to need it for the AP exam. You don't have to do it, but it's a good review. Like this is one that I would actually recommend. All right, that's it. I hope this video hasn't gone too long. It felt long to me. I'll try to edit it down the best I can. See you in a bit.